This is the lecture for Friday, April 17th. Today we'll be talking about medical isotopes. This literature was written by the American Nuclear Society. Here we see a pie chart showing the various uses of medical isotopes. About 99% could be characterized as medical imaging. We'll talk about the various things like gamma ray emissions or PET scans. Then 10% is used for actual therapy. We'll talk about internal radiation therapy, things like that. So, the US population is over 300 million people, and about 16 million nuclear medicine procedures are done each year. And there's various different ways that nuclear medicine is used. So one is just directly using radiation, okay, and let's talk about the various uses of radiation in general. So we can use radiation to sterilize medical products. So this is very relevant today with the global pandemic going on. We need to sterilize medical equipment. So today, over half of all medical equipment is sterilized using radiation. You can obviously sterilize using other techniques like heat. You can also use radiation for new drug testing. So over 80% of new drugs are tested using medical radioactive tagging. Okay, so essentially you replace a given element by a radioactive isotope, and then you can tag and you can track exactly where the various chemical pathways, either in the test tube or actually inside the body itself. Now you can use it for medical imaging. So approximately 68 million CT scans are performed in the U.S. each year. So CT scans are computerized tomography scans. We'll talk about that. Those are X-ray scans. And approximately 10%, so we can also use radiation for therapy, and approximately 10% of the medical procedures use radiation to treat diseases like cancers, heart disease, gastrointestinal disorders, and other types of disorders. So let's talk about medical imaging. We'll start off with the most familiar. So X-rays, you've all had X-rays, I'm sure. So these images are produced by placing the patient between an X-ray tube that's emitting the X-rays and a photographic plate. So the X-rays are passed through soft tissue but are absorbed by harder tissue like teeth, bones, and such. And so this can be used for X-rays of teeth, bones, and mammograms. Now, you probably have heard of MRIs, magnetic resonance imaging, or also nuclear magnetic resonance. So MRIs is basically using the nuclear spins, the precession of the spins. So you have, for MRIs, you have a very strong background magnetic field, and you also then have an oscillating magnetic field, some pulsed field, and so you can excite then the nuclear spins, they precess, and then you turn off the excitation and you measure the relaxation of these nuclear spins. And it turns out that the protons in water are very easily excited, so you get a nice mapping of the water, the distribution of the protons in water in a given tissue. And so you can see this nice image of the brain here. Now the computerized tomography scan, CT scan, so this is where you have X-rays being taken from many different angles, and then a computer puts these together to form a three-dimensional image, and then it can essentially give you slices through the three-dimensional object to cut away to show this tomographic image. Now we get to some more exotic types of medical imaging. So we have these radio tracers. So here is here's an image of a PET scan. So positron emission tomography, PET. So this is a slice of a brain of a man taken with PET. And so the red area shows where a significant amount of this tracer material was absorbed, and the blue shows the area where there's low or no tracer being absorbed. So what you do is you inject an isotope that decays by beta plus decays, that it emits a positron. Okay, so this positron will very quickly then find an electron in the surrounding tissue. It will annihilate and then form two gamma rays, two photons, gamma ray photons. And so what you then look for with your detectors is you look for two photons being detected in coincidence, coming back to back. They're flying out back to back, and so you can then very nicely localize where the photons came from, and determine where the positron was. Now you can also do this with something called single photon emission computed tomography. So this is where you use a radioactive gamma ray tracer. So you inject a gamma emitter into the subject, and this will then be absorbed into the tissues, hopefully selectively into the area that you're looking for, and then you look to see where the gamma rays are coming from. So this will work very much like the PT, but the amount of localization is not quite as accurate as for the PET scans, but it's actually much less expensive to do. And so this SPECT, or the SPECT imaging, you can see here a picture. You take a bunch of two-dimensional images from different angles, like in the CT scan, and then the computer then processes it into a three-dimensional image. Now, we talked about for the SPECT imaging, you need a gamma ray emitter, and we'll talk about a very important gamma ray emitter. So molybdenum 99 is the most in-demand medical isotope. It's actually not the molybdenum 99 that's being injected, but it's actually the decay product of molybdenum 99. So molybdenum 99 has a half-life of about 66 hours, and its decay product is technetium, metastable technetium 99, and it decays, and that's the gamma emitter, it decays by gamma ray decay into the ground state of technetium 99 with a half-life of 6 hours. And so that's very useful. The 6-hour half-life, it has a high radioactivity, so you can see a very nice signal, but then it's all gone over a very short period of time. And so now what the technetium does is it decays into the ground state. The ground state of technetium 99, it beta decays eventually, but that has a very long half-life, so it's for all intents and purposes stable. So there is actually a shortage of molybdenum 99. We'll mention now about 4 out of 5 molybdenum 99 generating nuclear reactors are nearing their end of service life, and so there's an effort to try to get new sources of molybdenum 99. It turns out that about 85% of all nuclear medicine examinations use this combination of molybdenum 99 and technetium 99 metastable for diagnostics of liver, lungs, and bones. So to try to ameliorate this shortage, there are various attempts to do non-reactor technetium production, or actually molybdenum production, where you there are various techniques. So here's one where you try to actually take molybdenum 100, which is more abundant than molybdenum 99, and so you then use a proton beam to produce technetium 99 directly this way. There are other approaches where you produce molybdenum 99 by doing things like uranium fission processes. So there is a company in Lansing, we've discussed it before, called Niowave, that's doing exactly this by doing uranium fission. So they take uranium and they induce the fission process through. They have these particle accelerators where they can do electron acceleration, and they can induce fission processes. Okay, now we can also talk about therapy, the use of radiation in therapy, and approximately 10% of all medical procedures use radiation. Okay, here's just a fact here. Today, radiation is used internally in the treatment of of other cancers, and nearly half of all nearly half of all cancer patients in the U.S. receive radiation therapy at some point in their therapy. Okay. So the first instance of the application of radiation for medical therapy was for thyroid cancer. So you can use iodine, which is absorbed in the thyroid very readily. So you use radioactive iodine-131, which is a beta emitter. And so what happens is then this radioactive iodine-131 gets lodged in the thyroid, and then it can be, that radiation will hopefully be localized and will kill the cancer in the thyroid. You can do various types of therapy. So you can do external radiation therapy, where you use an external beam to try to kill the cancerous growths. So, for example, you can have X-rays or protons. All right. Now, you can also use internal radionuclide therapy. Here, you would actually inject some source near the actual tumor that you're trying to kill. Typically, it's a gamma ray or a beta emitter near the target region. So various things like iridium-192 is used. Okay, this is often used for brain and breast cancer, and this is done using various wire forms that are introduced using a catheter into the target area, and then after you administer that dose, then you remove the implanted wire. You can also do this thing which I find very clever called boron neutron capture therapy. So this is very often used for brain cancer, gliomas, and so boron, it turns out, is readily absorbed into these tumor sites, and what you can do is use the fact that boron-10 in particular, is a very it readily captures neutrons. So what you can do is you can let the boron-10 be absorbed by the tumor, and then irradiate the region with neutrons. The neutrons will then mostly just pass through, but they will be captured by the boron, and then that boron capture of the neutrons will then so then you get boron 11, and then that will then decay into an alpha particle plus lithium-7, and so that will those alpha particles that are emitted will then destroy the malignant cells, and hopefully treat the cancer. Okay, now there's other types of therapy that one can do, and here's kind of a neat little picture of what's called gamma knife radiosurgery. Okay, so gamma knife radiosurgery looks something like this. You have this sort of like a wheel, like a bicycle wheel of gamma rays, and these gamma rays are being emitted by, for example, one example is radioactive cobalt. And so the whole idea is you're trying to target a certain region here with your gamma rays, but each gamma ray, though, is producing damage sort of all throughout the region. So what you're doing is you spread out the gamma rays so that you're not hurting the tissue too much here in the foreground, but everything is hitting the tumor that you're trying to target. So there's sort of a focusing upon that point here, so you deliver the maximum intensity then only in this region here. Now, we can also do the therapy using brachytherapy. So brachytherapy is the same thing as this internal radiotherapy. So it's basically the radiation source is placed near or inside the region requiring treatment. So this involves a precise placement of the short-range radioisotope near the site of a cancerous tumor. So very often you use a protective capsule or wire, and then it kills the surrounding tissue, and then eventually it's removed later, or in some cases it's allowed to remain in place for a prolonged treatment. Okay, so a key feature of brachytherapy is that the radiation affects a localized area around the radiation source. Now, they close by saying that, and here's a nice picture of the accelerated partial breast irradiation. is a form of brachytherapy that involves insertion of a radioactive source to kill breast cancer cells that may remain after lumpectomy surgery. And so they close by saying there is no doubt that medical research will find more clever ways for using radiation and radioisotopes to improve our lives. So I should mention that there's a shortage of these radioisotopes in the US. There's not really a lot of radioisotopes being produced at all in the US, and so one of the side benefits of EFRIB will actually be to produce these radioisotopes, and so there's a whole long list of radioisotopes that EFRIB will be able to produce. So, for example, the molybdenum-99 that we just mentioned. Some other very important ones are various things like radon-225 and others that we'll discuss tomorrow, or actually on Monday.